Magnetic field along the axis of the current loop. This is current loop placed perpendicular to the plane of the vapor. Its center is O and radius is A. This is the point on its axis where magnetic field is to be found. Now we consider DL current element here and the diametrically opposite current element here, and then we check its components. So let's write dB due to current element DL by using Biot-Savart's law. dB equal to mu naught upon 4 pi I dl sine theta divided by distance is s, so s square. Here theta angle will be angle between dl and s. So situation will be like this. This portion is dl and there is a line that touches it, so it will be 90 degree. So here, so we can say dl is perpendicular to s or theta equal to 90 degree. So we put sine 90 degree, that is 1. So we get dB equals mu naught upon 4 pi I dl divided by s square. Now we consider the components of dB. So there will be two components. One will be dB sine theta, dB sine phi in this direction, and then there will be dB cos phi in this direction. Similarly, there will be another dB due to this current element, this dB, and due to this current element, this dB, and this angle is phi. So dB cos phi will be in this direction, and dB sin phi will be in this direction. So clearly, dB cos phi component will cancel out, and dB sin phi component will contribute to the net magnetic field. So we can say that total magnetic field B is equal to integration dB sin phi. So we put the value of dB. dB is mu naught I dl upon s square, and sine phi from here perpendicular upon hypotenuse, that is A upon s. So now here we can put the limit from 0 to circumference of this ring, that is 0 to 2 pi a. So here 0 to 2 pi a, and integration of dl will give L, and when we put limits 0 to pi a, so we will get 2 pi a. So we write it mu naught I upon s cube times a times dl is L, limits 0 to 2 pi a. So it gives mu naught I a times 2 pi a divided by s cube. So mu naught I, and here 4 pi term is missing. So we should write here 4 pi, here also 4 pi, and here also 4 pi. So it will become mu naught I a square divided by 2s cube. Now we further simplify it. What do we get? We have got B equals mu naught I a square divided by twice of s. Here s can be found by using Pythagoras theorem. S equal to root of a square plus r square. So here we have s cube. It means we will get a square plus r square power 3 by 2. So this is basic equation. Now if there are n terms, then b will be equal to mu naught capital N I a square divided by twice of a square plus r square power 3 by 2. Now we can consider different cases. Case number 1. Case 1, suppose we want to find out magnetic field at the center of the loop. In that case, R will be 0. When R will be 0, then only we will get here AQ and then A square divided by AQ. So 1 upon A. So our answer would be B equal to mu naught Ni divided by 2A. Now, second case, when R is greater than A. In that case, A square can be neglected. Then in denominator, we will get R cube. So our answer will be B equal to mu dot N I A square divided by 2 pi, sorry, not 2 pi, 2 R cube. So it will be 2 R cube. And suppose we want to express it in terms of area, then area of the circle is pi r square. Here r is a, so we can introduce pi here, pi upon pi. Then we can write pi a square equal to capital A. Then our expression will be mu naught upon 2 pi r cube times n I a. Now consider third case when R and A are equal. If R and A are equal, in that case, we will get B equal to, here case 3, we are writing R equal to A. Then this will become A square plus A square. So that will become 2A square inside the square root, and then we will take 3 by 2 power. So we will get B equals mu naught N I divided by 2 power 5 by 2 times A. Now let's solve some numericals to understand it in better way. So the question is, the magnetic field due to current carrying circular loop of radius 12 cm at its center is this much, that is 0.5 into 10 power minus 4 Tesla. Find the magnetic field at a point due to this loop at a point on the axis at a distance of 5 centimeter from the center. So we know that B center is given by mu naught I divided by 2A, where A is the radius, and B axial we have just derived mu naught I A square divided by twice of A square plus R square power 3 by 2. So B axial divided by B center will be equal to, other terms will cancel out, and then we will get A cube divided by A square plus R square power 3 by 2, or B axial equal to B center multiplied by A cube divided by A square plus R square power 3 by 2. So here we are given A equal to 12 centimeter, that is 0.12 meter, R equal to 5 centimeter, that is 0.05 meter, and B center is also given as 0.5 into 10 power minus 4 Tesla. So B axial can be found. B axial will be, we can put these values. So 0.12 whole cube divided by, you can put other values. So it is 12 square, that is 144, and into 10 power minus 4. Here 0.12 square I have taken, and plus R is 5, that is 25 into 10 to the power minus 4. is equal to 5 into 10 power minus 2. So square of it. Similarly here, 12 into 10 power minus 2. Then whole power 3 by 2 times 0. 0.5 into 10 power minus 4. So if we simplify it, we will get 3.9 into 10 to the power minus 3 decimal. Now let's consider next question. Two identical circular coils of radius 0.1 meter, each having 20 turns, are mounted coaxially 0.1 meter apart. The current of 0.5 ampere is passed through both of them in the same direction, in the opposite direction. Find the magnetic field at the center of each coil. So let's write the information. Here we are given A equal to 0.1 meter and the number of turns are 20 and the radius is 0. Radius no separation between center 0.1 meter and the current is given as 0.5. This is separation between the centers because turning multiplicatively 0.1 meter apart. Now magnetic field at the center of each coil due to its own current. So let's see, V1 will be equal to mu naught Ni divided by 2A. Since we are considering the same coil and its radius is A and current is I, in that case magnetic field at its center will be given by mu naught Ni divided by 2A, where N is number of turns. So if we put the values, so mu naught is 4 pi into 10 to the power minus 7, number of turns are 20, into current is 0.5 divided by twice of A, that is 0.1. If we simplify it, so we will get 6.28 into 10 to the power minus 5. Now magnetic field at the center of one coil due to other. So let's find out V2. So V2 will be mu naught times Ni A square. So this is another coil and we want to find out magnetic field due to this coil at its center. So in that case mu naught Ni A square divided by twice of this separation is R. So twice of A square plus R square whole power 3 by 2. So we put the values 4 pi into 10 to the power minus 7 times 20 times 0.5 times 0.1 square divided by twice of A square, that is 0.1 square plus 0.1 square whole power 3 by 2. So this will become 0.628 into 10 to the power minus 7 divided by, in denominator we will get twice of 0.1 square whole power 3 by 2. So if we further simplify, so we get 0.628 into 10 power minus 7 divided by 2 root 2 times 10 power minus 3, and this will come to be 2.22 into 10 to the power minus 5 decimal. Now, when the currents are in the same direction, the resultant field will be sum of the two. So V will be total V1 plus V2. So we put the values of V1 and V2. So it will be equal to 6.28 into 10 to the power minus 5 plus 2.22 into 10 power minus 5, and that is equal to 8.5 into 10 to the power minus 5%. Now second case, when the currents are in opposite direction, then the net field V net in second case will be difference are the two. So V1 minus V2. So we put here minus sign. So 6.28 into 10 to the power minus 5 minus 2.22 into 10 power minus 5, and that will come to be 4.06 times 10 to the power minus 5 decimal. Now consider next question. Two coaxial circular loops L1 and L2 of radii 3 centimeter and 4 centimeter are placed as shown. Its radius is 3, its radius is 4, and their separation is 7 centimeter. And what should be the magnitude and direction of the current in the loop L2 so that the net magnetic field at the point O be 0? If direction of current is in this loop is in this direction, so in this loop current must be in the opposite direction so that the field produced must be equal and opposite, and hence they will get cancelled. So we can say that magnitude of field due to current in L1 must be equal to magnitude of field due to current in L2. So suppose current L2 is this direction, so direction will be just opposite. So it will be like this. So suppose current is I2. So we have to find out the value of I. So let's write the formula. The formula, the magnetic field at the axis of a current loop is given by mu naught I a square divided by twice of a square plus r square to the power 3 by 2. So we put the values mu naught I1 times a means 0.03 whole square divided by twice of 0.03 whole square plus separation, this is 4 centimeter. So 0.04 square whole power 3 by 2 must be equal to mu naught I2 or second loop magnetic field at this point. This is 3 centimeter and this radius is 4 centimeter. Mu naught I2 times 0.04 whole square divided by twice of 0.04 square plus 0.03 square whole power 3 by 2. So finally, the denominators of both are equal. So and mu naught will also cancel out. And I1 here, I1 is given in question 1 ampere. For cement places, what should be the minimum direction current? So that we can put here in question is incomplete. Given I1 equal to 1 ampere. So if I1 is 1 ampere, so let's write this value here. So we get 0.03 whole square times, and I1 is 1, so total product will be 1 equal to, and here I2 times 0.04 whole square. So it will be 9 upon 16 equal to I2. So we can say that I2 equal to 0.56 ampere. Thank you for watching.